we're coming to the end of the two-dimensional motion unit, which should be, it should make some of you guys very happy. Our test will be soon, but not this coming week. I'll let you know in class. All right, let's talk about vertical projectiles. The vertical projectiles are not that different from horizontal. You just have one more piece of information, and I'll tell you that when we get to it. But here's a kind of gives you an idea of what I'm talking about. It's an object that's launched upward at an angle, which we will call theta. This symbol right here is theta, stands for the angle, with some initial velocity, which I will call VI. Make that a little darker. VI, some initial velocity. Let me give you a few facts before I show you a diagram. So here are a few things you need to know. First of all, the initial velocity, again, which we call VI, is split into two components. That initial velocity, you have to split it into its x component and its y component. This language should seem familiar to you because we used the same language when we were doing our vectors, our little vectors unit. So you'll get a velocity that applies to the x-axis and a velocity that applies to the y-axis. And in just a moment, I'll refresh you on how to get these and what they mean. Alright, so a couple of things you need to know is that the velocity on the x-axis is used to move the object forward. Alright, so it's going to propel it forward. And then the velocity on the y-axis is used to move the object upward. So we have an object that's going forward and upward at the same time. And what happens is you get that parabolic motion. So let me show you a picture of that. You get that parabolic motion that looks like this. So this is what I'm talking about. You shoot something at some initial velocity down here, which we call VI. And here on the diagram it's V sub O, and O stands for not or original. Alright, so this velocity right here, you have to split it, because this velocity does two things. If you split it in two, part of this speed, part of this velocity, is going to be used to push the object upward, and then part of it is going to be used to push the object forward. It does two jobs, and you have to split it. And it is split according to the angle. If the angle is 45 degrees, then that velocity is split right down the middle. If the angle is less than 45 degrees, somewhere down in here, that means that this velocity is going to be used more toward pushing the object forward and less toward pushing it up. It won't go as high. If you have an angle greater than 45 degrees, then the velocity is being used to push the object high up and not as far forward. So you have to split the velocity because it does two things. And when you do that, what happens is the velocity on the y is that of free fall. Okay? So it starts off upward, then as it moves further, it gets a little smaller because that velocity is starting to slow down. Gravity has grabbed onto it and is pulling it down. And then at the very peak, the velocity on the y is 0. The velocity on the y-axis. We'll talk about x in just a moment. Then as you pass this peak, it begins to come down. So my y velocity, my arrow changes direction. And the more I fall, the bigger I get. So the bigger this velocity gets. Now again, the symmetry here is great. It's just like in free fall. If you take off and land at the same height, then this whole thing is symmetric, just like it was in free fall. If you remember, in free fall we had an object that went up. At the peak it stopped. Velocity here is 0. Velocity on the y-axis is 0. V is 0. Oh my gosh, I'm making it worse. Let me write it in pen. Velocity equals 0. Better. And then the object comes down And as long as it lands at the same height, the initial velocity that it had here is the same as the final velocity here, except over here it's positive and over here is negative. Same thing. If you shoot it and it lands at the same height, it falls in that same pattern. And the same pattern happened here. The time up equals the time down. That whole symmetric aspect of free fall will apply here to the projectile. So the same time it takes to get to the peak is the same time it takes to drop down to its original location. And you all know how to handle this. So the time up equals the time down. The velocity up, if I'm at the same location, it will be the same velocity except negative on the way down. And the velocity on the y at the peak is 0. So this whole conversation that I just did was talking about the velocity on the y-axis, and it's just like in free fall. Let's take a look at velocity on the x. The same thing, velocity on the x, just like in horizontal projectile, the velocity on the x is constant. So whatever it was after we split it in the beginning, it's going to stay that velocity all the way through, even at the top. At the top, the velocity on the y is 0. At the top, the velocity on the x is constant. So whatever it was in the beginning, it's going to remain constant all the way through the path until it lands. And so what we're doing is we're taking horizontal motion and vertical motion and we're looking at the whole thing. We just got done looking at horizontal projectiles, which started from here and came down. We hadn't looked at the beginning. Now we're going to look at the beginning and go all the way over. And when you get to class tomorrow, we'll have some questions, and hopefully when we get through the questions, you all will have some clarity. And I might even be able to sneak in a demo or two. So what are the equations involved? Well, the equations involved are the same. They are these equations. They're the same ones that you've seen for horizontal projectile. The only difference is that now we have an initial velocity. Okay, we have to have an initial velocity. If we don't have an initial velocity, then this object never gets in the air. If VI down here is 0, it never moves. So on a test, that is not a trick question. If I ask you what is the initial velocity, please don't put 0. It's not a trick. It has to be some non-zero number. Otherwise, you don't have a projectile. Alright, when we looked at horizontal projectiles, though, what we were able to do is get rid of this part of the equation because the initial velocity on the y was 0. That is not the case. Here, you have to have some initial velocity, like I said, in order to get the object to move forward. So now we can no longer neglect this part of the equation. We have to use it when it's necessary, but it may not always be necessary. Depends on how good you are at applying your physics. So let's take a look at some differences between horizontal and vertical projectiles. So here are some of the differences. First difference is that you must split the initial velocity, VI, into its x and y components, meaning you'll get a velocity on the x-axis and a velocity on the y-axis. Alright, the other thing is that anytime you have to deal with height, you need to use the velocity on the y-axis after you made that split. I'll show you that in just a moment. Anything that has to do with range or delta x, you have to use your velocity on the x-axis. So again, if it has to do with height, delta y, you're going to use velocity on the y-axis. If it has to do with range, delta x, you're going to use your velocity on the x-axis. And the same thing is true as in horizontal projectiles, is that time links the two. So the same time that you get for the y-axis, you can apply it to the x-axis. Those two things are the same. So how do we get velocity on the x and y? Well, that takes us back to vectors. Velocity on the y is the initial velocity sine of the angle. So if I take a look at this, I want you to see if you can visualize this very quickly. If I look at this beginning, you see how it's split? Basically, it is a right triangle. There's my y component, there's my x component, there is my angle, and here is my resultant. So I'm saying if I shoot this object at some speed, at some angle, part of it is on the x, part of it is on the y. How do you get the x component? Remember, for us, I said x was always cosine. How do I get the y component? Y is always sine. So, to get the velocity on the y-axis, it is the initial velocity sine of the angle. Let me write this as a reminder. R sine theta. And how do you get the x component? That's R cosine theta. The R in this case is the initial velocity, that very initial number before the split. Once you get these velocities, then you never go back to this number. Never go back to the initial velocity. You're either going to use velocity on the y or velocity on the x, depending on what it is you're looking for. Alright, so if you want to, you can rewind. If I've gone too fast, write down everything that I said. You can do the diagram. I hope you paused the video because I did say a lot and I did write a lot. So I hope you paused the video and took some time to think about what it was that I just said. But now I want to do a couple of sample problems so you can see what they look like. And I'll put a link to the hard copy in case you want to print and work along with me. So let's take a look at some samples. And the samples aren't always going to ask you, what is the maximum height? What is the time in the air? You're going to have to read the question and figure out what it is that it's wanting. But let's take a look at this one. This one's kind of fun. Jack be nimble, Jack be quick. Jack jumped over a candlestick with a velocity of 5 meters per second at an angle of 30 degrees. How long was Jack in the air? And did Jack burn his feet? Alright, so how long was Jack in the air? Let's take a look at that one. We're going to look for time. That's basically what we're looking for. T total. How long was he in the air up and down? I know my initial velocity is 5 meters per second, and I know he jumped at an angle of 30 degrees, and gravity is 9.8. And I'm looking for time total time in the air. That has to do with y, because time is based on the height. The higher you are, the longer you're in the air, so I'm going to look at my equations on the y-axis. And I do have a couple. I do know that the initial velocity at the top of the parabola is 0. So with that in mind, I'm going to use this equation right here. Final velocity on the y is equal to initial velocity on the y plus gt. And then I'm going to rearrange it and solve for time. But when I do, I get t is equal to final velocity on the y minus initial velocity on the y, that's an I, divided by gravity. Well, if I stop at the top, I know that the final velocity on the y is 0. I need to know what the initial velocity on the y is. And in order to get the initial velocity on the y, I have to split this velocity into its x and y components. Velocity on the y is r sine theta, which is 5 sine of 30, and velocity on the y turns out to be 2.5 meters per second. So the initial velocity is 2.5 meters per second. Now I can plug in my numbers. So I'm stopping at the top because I know at the top that the velocity on the y is 0. At the bottom it was 2.5, and I'm going to divide that by negative 9.8, and I get a time of 0.255 seconds. That was the time to go from the bottom to the top, but they want total time in the air, so I need to double that. So I need to do 2.55 times 2, and I get 0.51 seconds. This is total time in the air. And the second question is how high did he go? I want to know if he burned his feet. I know the candle is 0.25 meters. I need to know, did he jump at least 2.5 meters? So I need to know the height. I have my time, so really I can split this into two. I can split this motion into two. I know the time up, I know the time down, I know the height up is equal to the height down. I know that the velocity at this point on the y-axis is 0. So it's probably easy to look from here down. If I looked from here down, then this whole initial velocity is 0. So the original is delta y is equal to the initial velocity on the y-t plus 1/2 gt squared. I'm going to look coming down. When I do, this is 0. So 1/2 gt squared, 0.5 times 9.8, and I use half the time, 0.255, and that is squared. And once you plug it all in the calculator, you get the delta y coming down is 0.32 meters, and that has to be equal to the change in the height going up. Those have to be equal. So did he burn his feet? No, he did not burn his feet. I've gone a little bit over time, but I'm going to see if I can sneak this in. So let's do this one here. This one's not as bad as it looks. I have Ferdinand the Frog. He jumps from lily pad to lily pad. And I guess I must like 5 meters per second because that's what he does. And it takes him 0.6 seconds to go from lily pad to lily pad. So this t is the total time in the air. This has to be my delta x. So I already have some information. Delta x is 2.4 meters. T total is 0.60 seconds. And I need to know what the initial velocity is. That'll help me so I can find the angle, which is really what the question is talking about. Well, all the information that I'm given is on the x-axis. So why don't we turn to our equations for the x-axis? And there's really two. There is velocity on the x is equal to delta x over t. And then you have velocity on the x is equal to the initial velocity cosine theta. I have those two. Now with those two, I can work my way to theta. So let's get the velocity on the x first. Velocity on the x is 2.4, and I need to use the total time. 0.6, that becomes 4.0 meters per second. That's the velocity on the x. Well, I'm going to take that, I'm going to plug that back into there, and I can work my way toward cosine. Velocity on the x divided by initial velocity is equal to cosine of theta. And to get rid of the cosine, you do the inverse of that. So inverse cosine of velocity on the x times the initial velocity gives me theta. And that becomes velocity on the x4 divided by 5 is equal to theta. And if I inverse cosine both sides, I get theta is equal to 36.9 approximately degrees. And I went kind of fast. Go ahead and replay this section. I just wanted to get this done as soon as possible because I am running long. We'll have some questions in class, so save them until I see you. Good luck.